And it's obviously really useful to understand how molecules are breaking apart in plasma. So we are going to use a direct dynamics simulation to try and understand this process so that we can understand which bonds are breaking, how they're breaking, and we can use that then to possibly predict what the intermediate and final products are. And sort of in the long term, we're hoping that we can use this information to design molecules that will produce products that we properly desire. So the method that is being used, it was developed by Dmitry Shalashulin and Dmitry Markov at the University of Leeds. It's the ab initio multiple spawning method, which brings together the multiple cloning method and MCE. And it's quite a well-established method, and they've used it predominantly to do photo excitation simulations of singlet states. And the graph here is showing the dissociation of charge across this molecule. And so we're going to take this method and apply it to triplet states. So a bit about the method and how it works. So we start with potential energy surface in electronic state. We can label that state 1. And we're going to, for the sake of argument, just have a second potential energy surface, which we'll label state 2, but we could have more than that. And now we're going to construct our time-dependent wave function. The one amplitudes on 1 being the first potential energy surface, and 2 the second. And then we use a Gaussian wave packet, which are the things that we're going to move along these surfaces in time. And these follow Ehrenfest trajectories, which follow the average path between the two states. And we put together a wave function that has many of these, and we repeat our calculations multiple times to get an average view. We also introduced cloning, which says that at some point when the wave function is kind of equally split between the two potential energy surfaces, we basically double the wave function and place one onto one potential energy surface and one onto the other. So we, instead of getting just the average behavior, we're getting a combination, a better idea of it on each state. So how the method works is we calculate some electronic excitation cross sections using the Quantemol QEC software, and that gives us an idea of what our states 1 and 2 will be. And then we use the AIM method to propagate along, and we calculate the two different states using time-dependent density functional theory, using either QChem, and we're moving towards PySCF because it's open source. So here are the cross sections calculated using QEC for this hydrofluorocarbon. And we can see that the triplet states here dominate, so we're just going to focus on them. And the first kind of result that has been published on this is that very quickly, as we go from, we start in the two lowest triplet states, that the population falls very, very quickly into just the lowest triplet states. So to make our simulations easier and less computationally expensive, we can just start in that lowest triplet state, meaning that we only have to consider one of those potential energy surfaces. But there is the potential to consider more. And then with this method, we've calculated the dissociation at various different temperatures. These temperatures are considerably higher than you probably see in industry. in real life, but with this, we can see which are the kind of important dissociation channels. So we see lots of hydrogens coming off. We see much lower numbers of the carbon-fluorine bonds, and the carbon-carbon bonds here breaking sort of at rates somewhere between those two. So now we're just going to sort of go through some of the different hydrofluorocarbons that Ryan, who is a PhD student working on this, has been looking at. So with these 4 molecules here, we're seeing relatively similar numbers of bond breaking events happening across a 5 femtosecond period. So first, we're going to look at PPVE. So here we see that the carbon-carbon double bond breaks 70% of the time, which you might find surprising because it's the stronger carbon-carbon bond than the single bond here in black. We see quite low levels of the carbon-fluorine bond breaking, and we see just about 40% of the carbon-oxygen bonds. So about 1 of the 2 carbon-oxygen bonds breaking. But from this, we can look into the type of carbon-fluorine bond that is breaking. So the fluorine's furthest away from the carbon-oxygen bonds, and the carbon-carbon double bond break the least. And then as we move closer to those functional groups, we see the number of bonds broken increasing. Despite being very close, this terminal set of fluorines still break considerably smaller amount of the carbon-fluorine bond breaking, whereas this fluorine coming off makes up over 50% of the carbon-fluorine bonds we see broken. So here we're going to now compare 2 different isomers. So they have the same molecular formula, but they've got different structures. Just to make this particularly clear, we've got 1 fluorine environment here, 2nd fluorine environment here, and a 3rd fluorine environment here. And we have 4 different carbon environments. All of the carbons in the molecule are different. For the I isomer, we have these 6 fluorines are all in the same fluorine environment, and we have a 2nd one there. And then we have 3 different carbon environments here. So we can now compare the bonds being broken. We see that there's more of the carbon-oxygen bonds being broken in the I isomer. There's a greater number of carbon-fluorine bonds being broken. And we can summarize this in this chart here. So we can see that there are double the number of carbon-fluorine bonds being broken, a similar-ish number of carbon-carbon bonds being broken across both isomers, but a higher number of carbon-hydrogen in the I isomer, and a significantly larger number of the carbon-oxygen bonds being broken in the I isomer to the N. And if we just look at the carbon-carbon-carbon-oxygen bonds here, we can compare these to some mass spec data at the bottom. And we can see that the bonds that we're seeing broken correspond to the most common bonds that they saw in their mass spec that are being broken to get these kind of peaks down here. You're having to break these bonds that we're also seeing. So this really verifies that the method is producing results that you would expect. So some of the rules that we can take from this is that proximity to the oxygen means more fluorine bonds being broken. And this oxygen here is affecting this fluorine the most. And it also means that there's a sharper peak in the rate that these bonds are broken. And we can then sort of double down into this and look at which fluorines are coming off. And we can see that the majority of the carbon fluorine bonds are from this fluorine, and sort of similar levels from these environments here. And then for the N isomer, we see a similar pattern as before, that as we get further away from the oxygen, we see less breaking. And finally, we're going to look at this alcohol here, and we see that this hydrogen in the alcohol group comes off 90% of the time. It makes up a third of all bond breaking events. So this oxygen's having a large effect on whether this hydrogen comes off. But we see much lower levels of carbon fluoride. This set of hydrogens here we hypothesize, is acting as a buffer. It's stopping the effect of the oxygen being felt down the molecule, which is regulating how bond breaking events occur. So we've summarized these into a set of fragmentation rules. So the position of the oxygen atom is really important to how bonds break. And unsurprisingly, we see that hydrogens come off very quickly. That double carbon bonds dissociate more quickly than carbon-carbon single bonds, and that the effect of these groups can be kind of added together, that they aren't acting in isolation. So now we're going to look at TEOS. Again, we have calculated these the electronic excitation cross-section using QEC. And if we just sum together the singlet and the triplet cross-sections, we can see that the triplet excitation cross-sections dominate. So again, we're just going to look at the triplet states, and we're again just going to look at the first lowest triplet state. And these are the bonds that we see broken, that we're getting about one of the silicon oxygen bonds on average being broken, one of the oxygen carbon bonds being broken, and these carbon hydrogen bonds that are internal rather than on the end of the ligand. When we compare the two hydrogen environments that we have, internal and external, we see that the internal hydrogens, the ones closest to the oxygen, are coming off faster, and they're coming off with a much higher proportion than the ones on the terminal carbon. So that's consistent with the fragmentation rules that we had hypothesized earlier. So the software, the program that we've written, also can look at the final most common fragments that we put together. And we can sort of remove the slightly less interesting hydrogen and H2 fragments, and we proposed fragments from the TEOS dissociation. And these nicely, or a lot of them nicely, align with the set of proposed calculated fragments that were calculated using DFT based upon some experimental results that were published in this paper down here. there's sort of a slight discrepancy in the hydrogens and the way that we're calculating these final fragments. It's still quite a preliminary method. So using this AIM AIMCE MC simulation, we can show triplet dissociation, which hasn't really been able to be done before. We can show what the most common dissociation pathways are, and we're beginning to develop these rules for fragmentation. So where we can take this sort of in the short term, we want to optimize how we calculate these final fragments, and possibly as we only introduce fragmentation after the entire propagation has happened. Introducing fragmentation during the propagation step adds a layer of complication because of deciding how the multiplicity within the molecule splits. But in doing so, we might get more accurate simulations. And there is also the possibility of considering other triplet states in TEOS. It's a considerably larger molecule than the hydrofluorocarbons that we showed that considering only the first triplet state was necessary for. This could be possibly different for these larger molecules. In the medium term, we're going to accelerate the speed that we can do this by using a GPU, and also consider using some kind of machine learning technique to generate the electronic structure. We are doing a lot of repeated DFT calculations at each time step as we're propagating through, but there is actually very small changes within that. DFT has been simulated for singlet states quite effectively using machine learning techniques. So there should be a way to do that for triplets. And then in the long term, we want to use this method to generate large data sets that we can then use our fragmentation rules on, that you can start with a set of desired products or desired pathways to get to those products. And then we can build a model, build a molecule backwards from those. I think the next talk is going to be on some machine learning models that are already being developed that will hopefully be able to feed into this work. I'd like to thank the people who have done the majority of this work at the University of Leeds, Dmitry Shoshin, Dmitry Markov, and Ryan Brook, who's provided a lot of the results. In fact, most of the results that I've shown in this talk today.